Hello everyone, this is Letizia and I'm working as Senior Application Engineer in Low Frequency Electromagnetic Field at Altair. Today I'm going to give a presentation on Axial Flux Machine from input to results using macros with flux. These are the contents of the presentation. First, I'm going to do a brief introduction about macros in flux. Then, we will see in detail the geometrical parameters used by the macro. And I do a demo on how to use and how it works the macro dedicated to the axial flux machine. So, we will see some of the electromagnetic and thermal results that we can obtain with this macro. And at the end, I'm going to conclude the presentation giving you an idea of the computation time that you need to use this macro. Let's start with the introduction. So a macro is an high-level command added to the flux application, which regroups several commands in a given order. It receives upon entry one or more parameters and runs, upon exit, a series of predefined actions. It is an extension integrated into the software that you can find in a specific installation folder, going from the supervisor to the option, extensions, as in the picture. We collected a lot of macro during the years, and you can find the list going into the flux help at the right top of the screen. A macro file is a text file with Py extension which defines the macro function in the PyFlux language, and it is usually contained in a folder with a document that explains what it can do. So we need to use PyFlux language to create a macro that is a flux-specific language made by Python programming language plus Flux database and structure. So entities, commands, and some methods. We have a dedicated section in the help to discover more about them. The macro for the axial flux machine is particularly interesting because it encapsulates different sub-macro and thus improves the quality and efficiency of the user-software interaction for this specific case that requires a 3D model. In fact, while a radial motor in most of the case can be computed in a 2D domain, since the magnetic induction that go through the air gap can be considered constant along the path length and can compute it in the plane. In the axial flux machine case, this is not true, and we need the 3D domain to properly compute the flux line and so the magnetic field distribution. The purpose of the macro is to generate a generic geometry of an affair quickly, with almost all combinations of pulse pairs and slots, while editing most of the geometric parameters. The model considers periodicity and symmetry in order to save computation time as possible. So we are seeing an example model that is just a portion of the whole motor. Also, the three-phase electric circuit with its 3D winding is created. Let us see the geometric parameters in detail. We can find the inner radius rotor and the outer radius rotor, the rotor yoke length, the number of pairs poles, the space between magnets that are in percentage, just to avoid some error in the geometry, the height and the length of the magnets, the number of slots, the height of the slots, the thickness of the stator yoke, the height of the end slots, the opening slots, the Y slots, the space between slots and radius slots, and at the end, the length of the air gap. We can divide all the geometric parameters created in the model into main groups. The first one are the secondary parameters because depend on the primary ones that the user has to enter. The second ones are the primary parameters and extra parameters that define the shape of the axial flux machine. In this group, there are 3 parameters in red that should not be modified because they drive the configuration. And S is the number of slots, and P is the number of pairs poles, and MBSIM, that is the number of sections that can represent the machine. The others can be modified to improve the shape of the motor. Let's see. In particular, we have some parameters that have its dual, like the SPM parameter that defines the space between the magnets. By default, this parameter and its dual have the same value, as we can see in the picture. However, if we want to, for example, if we want that the distance between the magnets is not constant, we can edit the SPM2 to have different distance along the radial direction and enter directly a value in the definition, like shown in the picture below. Similarly, the slot opening can be different along the radial direction. We can see the parameter OS and its dual. And the shape of the teeth can be asymmetrical in radial and circumferential direction. We can see in the data tree the parameters W1 and W2 with their duals. The last parameters that depend on the primary parameters are the inner and the outer radius of the stator. That depends on the inner and on the outer radius of the rotor. Let me show you how the macro works. First of all, we have to open the Flux Supervisor, select the 3D simulation context, click on New Project, choose the working directory, and start a new project. So, in a few seconds, the new model appears. Close the modeler context to go into the standard one, and in the data tree we find the extensions folder. In it there is macros, so we can load the macro dedicated to Axial Flux Machine. We have to choose the right folder and open it. Once the macro is loaded in the model, we can run it. The window with the geometric parameters that we've seen before appears, and we can change the default values. Let's change just some of them, like the number of pairs poles to 6, the number of slots to 18, the 8 slots to 9 mm, 9 mm also for the stator yoke thickness, 20 mm the width of the slot, and at the end 3 mm for the air gap. Clicking on OK, the macro starts and builds the parametric model of the axial flux machine with the values that we entered. After a few seconds, the sketch context appears in order to create the two parts of the motor, starting with the rotor one. We can see the building of the magnets, of the rotor yoke, the model is built considering periodicity and symmetry to save computation as possible, so the portion or the period depends on the configuration that we choose. In this case, with 6 pairs poles and 18 slots, we have only 60 mechanical degrees represented. Once the rotating part is complete, the macro starts to create the teeth, 3 in our case. To continue, the stator yoke is extruded and the bases of the teeth are built in 2D before create the slots. Also, the portion of air around the rotor that allows us to define the rotation is built, similarly to the sliding line that we are used to use in 2D domain. The last geometry added is the infinite box to automatically apply the boundary condition at the model. At the end of the process, other macros are loaded to add winding and circuit to the model. Once these secondary processes are finished, we can find the macros that allows us to define different computation in automatic way. The model is in fact just the starting one to perform electromagnetic analysis. The macro finished because we can see the green light at the bottom of the screen, and in a few minutes we finally have not only the complete parametric geometry, but also the physics of the model. Now we can decide to perform the first computation, for example, BACK-EMF and Cogging torque, clicking on this macro and run it. We have just to enter the parameters that the window requires. This is similar for each macros here that allow us to compute electromagnetic analysis on this model. Instead, if we want to perform thermal analysis, we have to load the new macro that is in the same folder like before. So, Altair thermal, mag term, and run it. This macro starts from the beginning to build the new model for thermal computation, adding insulation and coils to the model to compute temperature in them, and add automatically two new macros for the thermal computation, for the steady state and the transient one. So at the end, we can have the two models ready to solve for the electromagnetic computations and for the thermal ones. All the computation are carried out by a second macro that is automatically loaded in the model, as we've seen, except for the short circuit test that is necessary to load it manually. In this scenario, no current is flowing through the stator coils, while rotor turns at constant speed. As output, we have the Cogging torque and the BACK-EMF shape. For the constant speed simulation at the working point, we supply the motor with a three-phase balanced current. To see the curve of the torque, the magnetic induction in the magnetic circuit, and other quantities like Joule losses, iron losses, etc. In the starting analysis, we can see the mechanical and electrical behavior of the motor with the curves of rotational speed and acceleration, and the currents flowing through the coils. In the short circuit case, as default output, we have the curve of currents flowing through the coils and the torque during the faults. As last computations that I want to present you, we finally have the efficiency map, the losses maps, the current and voltage maps, but also the LD and LQ tables that are quite useful to express the behavior of the motor in a system model simulation to design the control of it. To complete the types of analysis that we can perform with the Axial Flux Machine, we have the thermal ones. One dedicated macro translates the geometry generated for the magnetic problem into another suitable for the thermal analysis and loads the two macros needed for the thermal computation. In the transient thermal analysis, the thermal behavior is studied at normal working conditions, providing iron and eddy current losses and as inputs. As output, the temperature in all the domain represented as ISO values for each step and the maximum temperature in the coils or other parts of the motors versus time can be plotted. In the steady-state computation, the thermal behavior is studied at normal working condition, with a constant initial motor temperature equal to 20 centigrade, while the simulation ends when thermal steady-state is achieved. As output, the temperature in all the domain once final motor temperature have been reached. So to conclude, the AFIR macro is an efficient tool set for modeling axial flux machine that allows the user to give accurate results, drastically reducing the modelization time. Considering the BACK-EMF, the constant speed, and the steady-state computations, we took just half of the day to see the first results. Sure, the solving time depends on the configuration that you choose, and so on the number of nodes that you have in the model. But to give you an idea of the computation time of the presented model, it took 10 minutes for the construction, 1 hour and 25 minutes for the Cogging and BACK-EMF computation, and 35 minutes to obtain the torque at constant speed, and others 10 minutes to carry out a thermal analysis in steady-state condition, considering the building of the thermal model too. At last, the parametric models can be easily used with hyperstudy to perform the optimization of the axial flux motor. So, I hope this webinar was interesting, and before closing, please let me know if you have any questions.